Okay, today is more of 3.4. It's just using derivatives to find velocity and other rates of change, depending on the problem, just a couple different ones. First one's write the circumference in terms of the area of a circle. So in order to do that, you need to write down both formulas for a circle. Circumference is 2 pi r, and then area is equal to pi r squared. Now, hopefully you guys are getting good at knowing how to turn one into the other. I know this has been tricky for some of you. We need circumference is equal in terms of the area. So there's no area here, but there is a radius. So that means for this equation here, we have to solve for r. So when you do that, you get r squared is equal to a over pi. Then we can take the square root and say r is equal to the square root of a over the square root of pi. And I'm going to leave it like that for now. And then we're going to rewrite circumference over here by subbing this in for r. So c is equal to 2 pi times the square root of a over the square root of r. So that is the, over the square root of pi, I should say. So that is the equation for circumference in terms of area only. Now, what they want you to do is first find the rate of change. So part A is find the rate of change, which again, that word should mean derivative to you guys. So we're going to take the derivative of c with respect to A. First, I'm going to rewrite it so it's easier to take the derivative. I'm going to put all the constants over here. So those are all constants. And then I'm going to rewrite a as a to the 1/2 power, so I can use the power rule. So if I take the derivative, I am now going to call this dc over dA, change in circumference with respect to the area, is equal to, multiply this by 1/2, remember that goes down, so that just becomes pi over root pi times a to the negative 1/2. Or, that means that goes down and under a square root, you could just rewrite it as dc over dA is equal to pi over the square root of pi times a. So that is what happens. That is how the circumference is changing with respect to the area. Okay, so part B now, once you have the formula, you now are just plugging in the numbers. We have 4 pi for area and 16 pi. So when it's 4 pi, the change in circumference becomes the square root of pi times 4 pi, which is equal to pi over, there's a pi squared, square root of that is a pi, and square root of 4 is 2, which is just equal to 1/2. And the units for this, we don't have units, but it would be units of circumference over units of area. So if it's inches, it'd be inches over square inches. So every 1 unit of circumference that changes would change that area by 2 units, or vice versa if you want to say it the other way, when the area is 4 pi. When the area is 16 pi, the circumference is changing at a different rate. So we put that in, and we get the square root of 4 pi times 16 pi, which is equal to pi over, pi times pi is pi squared, square root is pi, square root of 16 is 4. These cancel, so we're left with 1/4. So when the area is bigger, the change in the circumference is not as much as when the area is changing, because the circle's already bigger, so it's not changing as much. Okay, that's how you can do problems like that. This is a basic just plotting and then estimating. Remember, estimating is doing derivative, but you do not use any derivative formula. You use basically the slope equation, changing the rate of change between 2 points. First, let's just plot this and see what it looks like. I'm going to do a quick sketch of this just because. So this is going to be feet, my position in feet. This is going to be my time in seconds. 1, 2, 3, 4. And what does this go up to? 27, and it goes down to -10. Alright, I'll go by 5s then. 5, 10, 15, 20, 25, 30, -5, -10, -15. So these go by 5s on this axis. So 0, 3.5, 0.5, -4, 1, -8.5, and 1.5 is -10, 2. So it looks like it's a standard parabola. Yeah. I mean, obviously my spacing isn't perfect, so 3.5 goes all the way up to 14 now. This is something a little bit newer. And then 27.5 way up here. So it looks something like this. Okay. And we're supposed to estimate the velocity at 1, 2.5, and 3.5 seconds. Well, at 1, hopefully you guys, just by looking at the graph, remember the velocity is, if this is position, it's the slope of the curve, which is negative. So we should get a negative velocity at t equals 1. So at t equals 1, we're going to do our velocity is going to be equal to the change in position over change in time. So that means that I want the position at 1.5 minus the position at 0.5 all over 1.5 minus 0.5. So those numbers are, the position at 1.5 is -10, minus at 0.5 it's -4, all over 1.5 minus 0.5 is 1. So you get -10 plus 4 is -6 feet per second. And that makes sense. We got a -1. Okay? So at 2.5, same thing. I'm not going to write this whole thing out. Look for 3 and 2. Those are the ones that bracket 2.5. So the position, and it should be, by the way, at 2.5 a positive slope. So we're going to do from 3 to 2. So 3.5 minus -8.5 over the change in time, which is 3 minus 2. So 3.5 plus 11 and 8.5 is 12. And then if we do estimate it at 3.5, it looks like it's going to be even steeper. And I'm just going to, at 3.5, I'm going to use 4 and 3 to bracket that. So it's 27.5 feet minus 3.5 feet all over 4 minus 3. So 27.5 minus 3.5 is 24 feet per second. Which again makes sense because it's going up faster. Alright, so that's how you get velocities off of points. Remember, you take either side, find the slope. Alright, last problem. Melissa's back from last year. She survived her crash and is flying again. She fires her retro rockets, causing the ship to slow down, stop, rise up again, then come back down. Her displacement in kilometers from the surface of the moon is found to follow that equation. So write equations for velocity and acceleration. Hopefully at this point you guys know that velocity is just the derivative of this, and then acceleration is the derivative of that. So we're going to do that first. So for part A, I'm just going to write it down. The velocity with respect to time is equal to y prime, which is equal to, using the power rule, -0.03. That becomes t squared, plus 2t minus 20. The acceleration is equal to the derivative of velocity, which is equal to -0.06 t plus 2. So that's part A. Part B. Find the acceleration at time t equals 15. At that time, is the spaceship speeding up or slowing down? This is a very important question that everyone will get wrong. No, not necessarily, but you have to remember this. So let's find the acceleration first at 15. So the acceleration at 15 is equal to -0.06 times 15 plus 2. Okay? When you do that, you get 1.1 kilometers per second. Now, a lot of you guys will be tempted at this point to say, oh, the ship is speeding up because the acceleration is positive. That does not mean that the ship is speeding up. Okay? You need to also check velocity. Important. Because in order to be speeding up, it has to be traveling in a direction, and then the acceleration has to be happening in that same direction. So if you're moving backwards but accelerating forwards, you're not speeding up, you're slowing down. So you need to check velocity. So the velocity at 15 is equal to negative 0.03 times 15 squared plus 2 times 15 minus 20, and you get that to be 3.25 kilometers per second, which means since they are both positive, the ship is speeding up. In the positive direction, which is probably away from the surface. Yeah, it's away from the surface. So, part C, find the values at t at which the spaceship has stopped. Okay, well, that's simple enough. In order for it to be stopped, the velocity has to be 0. So I'm going to set the velocity equation equal to negative 0.03 t squared plus 2t minus 20. Now at this stage of the game, I'm going to just kind of, because I don't want this video to be too long, at this point just use your calculator, graph it, and do, find the intersects, or find the zeros. And you get that it happens at t equals 12.251 seconds and at 54.415 seconds. Okay, but the key here is setting the velocity equal to 0. And finally, when does the spaceship touch the surface of the moon? So when is the position 0? Again, that's another one where you can look at your graph. This time graph position, so you'd want to have the position equation into your y1. So this would be in your y1. And this would be in your y2. And you just figure out again, when you use the calculator, it hits at t equals 77.531 seconds. And the question is, what is the velocity? And then explain what you think happens to the spaceship. So now to find the velocity at that time, you plug that in, and you get negative 45.270 kilometers per second. Just think about that for a second. In 1 second, the spaceship is traveling 45 kilometers towards the moon. Okay? I don't know the exact conversion. I think it's like 1.6 kilometers per mile, 1 mile. So whatever that is, it's probably like 30 miles per second. Imagine going 30 miles in a second. So because of that, what do you guys think happens when the spaceship hits the moon? Well, it'll probably disintegrate because it's going way too fast. So again, she will crash. Okay. Alright, so those are the extra problems from 3.4.